Model evaluation techniques are methods used to assess how well a machine learning model performs. These techniques vary depending on the type of task, for example, classification, regression, clustering. Here's a structured overview. Classification tasks. Holdout validation. Train/test split, for example, 80-20 or 70-30 fast, but can lead to high variance depending on the split. K-fold cross-validation. Data is split into K-folds. Model is trained on K1 folds and tested on the remaining fold. Reduces variance and gives a better estimate of model performance. K-fold cross-validation is a technique used to evaluate the performance of a machine learning model more reliably than a single train test split. It helps ensure the model's performance is not dependent on how the data was split. How it works, step by step. 1. Split the data into K equal parts, called folds. For example, if you choose K equals 5, the data is divided into 5 folds. 2. For each of the K rounds, folds. Use K-1 folds for training. Use the remaining fold for testing, validation. Train the model on the training folds. Evaluate it on the validation fold. 3. Repeat this process K times, so that each fold is used exactly once as the validation set. Collect the evaluation scores, like accuracy, F1 score, etc., from each fold. 5. Average the scores across all K-folds to get the final performance estimate. Stratified K-fold cross-validation. Like K-fold but preserves the percentage of samples for each class. Useful when dealing with imbalanced classes. Stratified K-fold cross-validation is a variant of K-fold cross-validation used in machine learning to evaluate model performance, particularly when dealing with imbalanced datasets. It ensures that each fold in the cross-validation process maintains the same class distribution as the original dataset, providing a more reliable estimate of model performance, according to Geeks for Geeks and LinkedIn. Key features and benefits. Handles imbalanced datasets. Stratified K-fold is particularly effective when one class is significantly underrepresented compared to others, ensuring that each fold reflects the true proportion of each class. More reliable performance estimation. By maintaining class distribution, stratified K-fold provides a more robust estimate of model performance, especially when evaluating classifiers on imbalanced data. Improved accuracy metrics. It can lead to more accurate and reliable accuracy metrics, as it avoids the biases introduced by random splits that might disproportionately affect one or more classes. Enhanced generalization. Stratified K-fold helps to ensure that the model generalizes well to unseen data, as it's trained and evaluated on data that mirrors the real-world distribution of classes. How it works. 1. Data splitting. The dataset is divided into K-folds, but unlike regular K-fold, the division ensures that each fold contains roughly the same proportion of each class as the original dataset. 2. Model training and evaluation. For each fold, the model is trained on the remaining K1 folds and evaluated on the held-out fold. 3. Performance averaging. The model's performance is averaged across all K-folds to provide a final performance estimate. When to use. Imbalanced datasets. When the class distribution is significantly uneven, stratified K-fold is a crucial tool for evaluating model performance. Classification tasks. It's commonly used in classification problems to ensure that each fold accurately reflects the true class distribution, situations where generalization is important. When the goal is to train a model that generalizes well to unseen data, stratified K-fold helps to prevent overfitting to a particular class. Example. If a dataset has 80% of one class and 20% of another, stratified K-fold will ensure that each fold also contains approximately 80% and 20% of those classes, respectively, according to Geeks for Geeks. Leave one out cross-validation, Luakiv. Extreme version of K-fold with K equals n, number of data points. Very accurate but computationally expensive. Leave one out cross-validation, Luakiv, is a special case of K-fold cross-validation where K equals the number of data points. That means each fold contains just one data point for validation, and the rest are used for training. How it works, step by step. Suppose you have n data points. For each of the n iterations, take one data point as the validation set. Use the remaining n-1 data points for training. Train the model and evaluate it on the single validation point. Repeat this n times, each time leaving out a different data point. Average all n results to estimate overall performance. Example. If you have 5 data points. Iteration 1. Train on, 2, 3, 4, 5. Validate on, 1. Iteration 2. Train on, 1, 3, 4, 5. Validate on, 2. Iteration 3. Train on, 1, 2, 4, 5. Validate on, 3 and so on until all points have been used as the validation point once. Pros. Uses as much data as possible for training. Good for very small datasets. No randomness, results are deterministic. Cons. Computationally expensive, especially for large datasets, since you train the model n times. Can have high variance, each validation is based on just one point. Evaluation metrics. Accuracy. Proportion of correctly predicted labels. TP plus TN. Total. Precision. TP. TP plus FP true positives is divided by sum of true positives and false positives. TP, true positives, is the number of correctly predicted positive cases. A false positive occurs when a model incorrectly predicts the positive class for an instance that is actually negative. Precision is especially important when false positives have serious consequences. For example, spam detection, medical diagnosis. Example. Suppose a binary classifier is predicting whether emails are spam, positive, or not spam, negative. Recall. Sensitivity. TP. TP plus FN F1 score. Harmonic mean of precision and recall. Confusion matrix. Breakdown of actual versus predicted labels. A confusion matrix is a table used to describe the performance of a classification model by comparing actual versus predicted outcomes. ROC curve and AUC, for binary classification, shows trade-off between sensitivity and specificity. 2. Regression tasks. A. Cross-validation methods. Similar to classification. K-fold, Lukiev, etc. B. Evaluation metrics. Mean absolute error, MAE. Average absolute difference between actual and predicted. Mean squared error, MSE. Average squared difference. Root mean squared error, RMSE. Square root of MSE. R-squared score, coefficient of determination. Measures proportion of variance explained. 3. Clustering tasks. A. Internal evaluation. Silhouette score. Measures how similar a point is to its own cluster versus other clusters. Davies-Bouldin index. Lower is better. Compares intra-cluster distance with intercluster distance. Dunn index. Higher is better. Ratio between minimum intercluster distance and maximum intracluster diameter. B. External evaluation. If ground truth is known, adjusted RAND index, ARI normalized mutual information, NMI Falks-Mallows index. 4. Time series tasks. A. Walk-forward validation. Train on data up to time t. Validate on time t plus 1. Respects temporal ordering. B. Time series cross-validation. Rolling origin or expanding window schemes. C. Evaluation metrics. MAE, MSE, RMSE, same as regression mean absolute percentage error, MAPE. 5. General tips. Use Bayesian models for example, always predict majority class or mean. Visualize results, for example, confusion matrix, error histograms. Check for overfitting/underfitting using train versus validation scores. Use multiple metrics for a comprehensive picture. In machine learning, the ROC curve and AUC are important tools for evaluating the performance of binary classification models. What is the ROC curve? ROC stands for Receiver Operating Characteristic. It is a graphical plot that illustrates the diagnostic ability of a binary classifier as its discrimination threshold is varied. What is the AUC? AUC stands for area under the curve, specifically, under the ROC curve. It is a single scalar value that summarizes the overall performance of the classifier. Range, 0 to 1. 1.0 perfect classifier. 0.5 no discriminative power, random guessing less than 0.5 worse than random, the model is likely reversing predictions. Example. Suppose you have a classifier that outputs a probability score, not just 0 or 1. By applying different thresholds, for example, 0.1, 0.2, 0.9, you can calculate the true positive rate TPR and false positive rate FPR for each threshold and plot the ROC curve. True positive rate is also called recall or sensitivity.